Hello, today's lesson we are starting chapter 6 on differential equations. Today we're focusing on slope fields as an introduction. And so our goals today are to use initial conditions to find particular solutions of differential equations. And we're also going to talk about how to use slope fields to approximate solutions of differential equations. So what are differential equations? They are equations that involve x, y, and derivatives of y, and they can be used to describe radioactive decay, population growth, Newton's law of cooling, and many other phenomena. And so we're going to see some examples of that in the next section. An example of a differential equation is here. An example might be 2xy prime minus 3y equals 0. Sorry, it's on two separate lines. And so when we talk about solutions to differential equations, our solutions are going to be functions, and we have different types of solutions. So if there's only one function that works, we call it a singular solution. If we can generalize it and have maybe a parameter, such as a constant or something, we call that a general solution. And if we use initial conditions to solve for that parameter or that constant, we call that a specific solution. And we can also talk about the order of differential equations based on the highest order derivative that appears in the differential equation. So mostly we'll be working with first order differential equations such as y prime equals 4y, but you may also have some second order differential equations where you see a second derivative equal to something. So let's do some examples so you can get an idea of how differential equations work and the different types of solutions. So our first example today is determine whether each function is a solution of the differential equation y double prime minus y equals 0. So this is a second order differential equation, and we need to basically go through each of these and figure out, do they satisfy that or not? So let's find the second derivative and plug it into my differential equation and see if it works. So my first one, I have y equals sine of x. So then y prime would be negative cosine of x, and not negative cosine, regular cosine. Cosine of x, and then my second derivative is that's where the negative is. So then I get negative sine of x. And so then if I plug it in, I get y double prime minus y is going to equal, let's see here, negative sine x minus sine x, which gives me negative 2 sine x, which does not equal 0, so my answer is no, this is not a solution. For b, if we have y equals 4e to the negative x, and I take the first derivative, I'm going to get negative 4e to the negative x, and my second derivative, I'm going to get 4e to the negative x, plug it into my differential equation, y double prime minus y, and I get 4e to the negative x minus 4e to the negative x, which does equal 0, so this would be a solution. And my last one is very similar to that, but I have a constant c times e to the negative x. And so if I find my first derivative, I get negative c to the negative x. My second derivative is c e to the negative x. Plug it into my differential equation, and I'm going to get c e to the negative x minus c e to the negative x, which equals 0. So this is also a solution, and this is what we would call the general solution, because it describes the form of all possible solutions. So that's the general solution. And then if they gave us a particular value for x and y to start with, then we can find the specific value of c, such as 4 might be a particular solution. All right, let's look at the next example. Finding a particular solution. So if I have the differential equation xy prime minus 3y equals 0, verify c times x cubed is the solution, assuming x is greater than 0, then find the particular solution determined by the initial condition y equals 2 when x equals 3. All right, so here's what we're going to do for this one. So the first thing we want to do is we need to verify. So I need to find y prime. So if I have y equals cx cubed, then I have y prime is going to equal 3cx squared. And so then when I plug it into my differential equation, x times y prime minus 3y, I am going to get, let's see here, I get x times 3cx squared minus 3 and then y was cx cubed. And so then I get, let's see, then I get 3cx cubed minus 3cx cubed, which equals 0. So there we verified it. Okay, next step, find the particular solution when y equals 2 and x equals 3. So if I have y equals cx cubed and I plug in those values, I get 2 equals c times 3 cubed. So then I'm going to get c equals 2 divided by 27. So my particular solution would be y equals, and then my value for c, 2 over 27 x cubed. And then we have to put our little parameter here that x is greater than 0. Great. And then if I look at this, here's what that solution might look like if I was to graph it, and we make sure that we do not include anything in quadrants 2 or 3 because we don't want any negative x's. Slope fields. Slope fields are a lot of fun. I really enjoy slope fields, and I hope you do too. So when we talk about slope fields, what we're doing is we're considering all of the possible general solutions. And so we're going to kind of graph what they might look like and get a feel of what that graph flow could look like, which is pretty cool. So if we have our differential equation y prime equals some function of x and y, what we can do is we can plug in x and y values and find what the slope is at that one particular point. And so a slope field then means we just make little short segments at those points of those slopes, and then we can kind of get a feel of what the whole graph would look like. So let's do an example. So sketch a slope for a field of the differential equation y prime equals x minus y for the points -1, 0, and 1. All right, so first thing I'm going to do is I'm going to find the slope at -1, 1. So then y prime equals -1 minus 1, which is going to be 0. Wait, did I do that wrong? Yes, I did. -1 minus 1 is -2. Fantastic. The slope at 0, 1 is going to be y prime equals 0 minus 1, so I get -1. And then the slope at 1, 1 is going to be y prime equals 1 minus 1, and that's the one that's equal to 0. So then if I want to do a slope field for these, what I'm essentially doing is I'm looking at the xy plane here. And let me make my tick marks every 3 boxes here so we have some space to work with. Oops. Yeah, that's 3. Okay. 1, 2, 3. Okay, so put 1, 2, 3, 1, 2, -1, -2, -1, -2. Okay. So my at -1, 1, so when I'm here, my slope is going to be -2. So my slope is going to be kind of steep like this. Great. And we're just going to make a little segment with a slope of -2. At 0, 1, right here, my slope is -1, so a little less steep. And then at 1, 1, my slope is 0, so I'm just going to put a little flat line. And so what we can do is we can continue that pattern to fill out the field, and that's called a slope field. So let's look at some examples and identifying. So we're going to match each slope field with its differential equation. So the first one is y prime equals x plus y. The second one is y prime equals x. And the third one is y prime equals y. So let's see here. I'm going to look at B. I'm going to see if I can identify B first. Because if I look at B, I'm looking for the slopes that are just the same as the x coordinates. So that means when I go up and down vertically for my x values, all the things should be the same. So let's look at these. So I have, looks like the second one is the one changing the most in terms of x and y coordinates. So A, though, if I look, all of these have an x coordinate of 0, and they all have a slope of 0. All of these have an x coordinate of 1/2, and their slope is approximately 1/2, it looks like. So this would be graph B. Then I'm going to try and identify y prime equals y. So I'm looking at the same thing, but now I'm looking at the y coordinates. All of these points have a y coordinate of 0, and they're all flat. All of these have a y coordinate of 1, and they all have a slope of about 1. And then it gets steeper if I go higher. So y coordinates of 2, a little steeper. So this one would be graph C. And then if I want to look at the last one, I have y prime equals x plus y. So if I pick, let's say, this point right here, right? So that would be 1, 1, and y prime would equal x plus y would be 1 plus 1, which is 2. That looks about right. And if I had 0, 0, I'd want it to be flat. And if they're both negative, I'd want it to be negative. And then along my diagonal, y equals negative x, I would want them all to be flat, which it is. So this would be graph C. A. Right? Is it A? Yeah, it's A. Great. Fantastic. All right, our last example. We're going to go ahead and sketch a slope field for the differential equation y prime equals 2x plus y. And then we're going to use our slope field to sketch the solution that passes through the point 1, 2. All right, so here's what we're going to do here. The best thing that's kind of easy to do is to go ahead and make a table. So if you make a table of your x and y, you can do this however you want. I prefer tables, just because it's how my brain works. So if I have x, y, and then my y prime, which is 2x plus y, and then you can figure out kind of what you want. So maybe for your x's, you want to go -2, -1, 0, 1, and 2. And then for my y's, let's see here. You can pick more if you want. You can do these on your, well, I don't know if you can do these on, yes, you can probably do these on your calculator. Not quite sure how. Okay. You can do more. And then if I want to, I can pick -1, and then 1, -1, 1, -1, 1, -1, 1, -1, 1. So we can get kind of a feel of what's going on. And we can plot a few more points later if we want to. So if I plug those in, so 2 times -2 plus 1, give me a -5. 2 times -2 plus +1, -3. 2 times -1 plus -1 is -3 again. 2 times -1 plus 1 is -1. 2 times 0 plus -1 is -1. And 2 times, there we go, got another one. And then if I have 2 times 1 minus 1 gives me a 1. 2 times 1 plus 1 gives me a 3. And then I have 2 times 2 times 2 plus -1 gives me a 3. And 2 times 2 plus 1 gives me a 5. Okay, fantastic. So this gives us some points to work with here. And so here I kind of have the answer so we can skip. So if we look, we can go to the points. So what you would do on your graph is you would go to the point -2, -1, and you would say, oh, I want to draw a little segment at that point that has a slope of -5, so it'd be pretty steep, okay? And then you would go to -2, +1, and you would say, okay, at that point, I want to draw a slope that's still steep, but not quite as steep as the one right below. And you would fill out these segments all throughout, and you would get a graph that looks like this one here. And so then the rest of the question, so that's called the slope field, okay? And the rest of the question said, sketch the solution that passes through 1, 1. So if I find the point 1, 1, so let's see, each of these tick marks is a half. So 1, 1 is right here. And then I kind of follow those segments, right? They're kind of like connect the dots. So it kind of goes steep down, and then I see that I'm going to change and go up like this. Something like that. Maybe even goes down a little bit. And these are just approximate solutions. Like, you don't know. Who knows? Let's see. It goes down. Looks like it kind of, I'm not doing steep enough. There we go. It goes down like this and then up there. Something like that. All right. So you can kind of see how those solutions would look. And so, but depending on where you start, would kind of fill out the rest of the graph. And there's this great tool in Desmos, which is a slope field generator. I will post the link on Schoology for you so you can check your answers to your